Hi there, so it's me, Jose. It's been over a year since I posted my last video. Um, yeah, so it's been a while. I really want to make a comeback, and I would love to start posting videos about CUDA right now because it's something that has piqued my attention lately, and I would love to make a few tutorials about that. But we're going to start with the easiest possible introduction to CUDA. All the credit goes to this awesomely and very impressively skilled person, Mark Harris, a distinguished engineer at NVIDIA. He's made some very cool tutorials, not only this one. So there are a few here. So these few over here seem to be boring stuff that it seems to be important. If I'm allowed to say that. Same with this one over here. So yeah, all of this. This probably would be worth a tutorial on their own. There's also one for matrix transpose stuff. That one seems to be very interesting, very foundational. And there's like a couple of them for finite difference methods in CUDA. So this one would be very cool to make a tutorial about, these three over here, these ones. It would be cool to make a tutorial for about scientific computing, which is the topic of the context. And there's another topic here that maybe we can include in the boring stuff. There's boring stuff that is important, that is worth learning too. But obviously what excites me the most is these three over here. But that's for the future. In this tutorial I'm going to focus on the introduction. So this is going to be the easiest introduction to CUDA you will ever come across. We're going to focus, by the way, in doing it. We're going to focus on the code. I don't want to focus on the setup. So we're going to focus in Google Colab for that purpose, because it's the easiest setup. There seems to be a little issue though, since March 12, 2025 or around that time, in which the versions, the 12.5 version seems to be having some sort of issue. So this guy over here figured it out. Yeah, 12.5 has some sort of issue when you try to run certain features of CUDA, but I will teach you how to take care of that too. Anyways, so we're also going to get some help from ChatGPT. I think it's going to be helpful for explaining a few things too. So let's go for it, okay? So the easiest introduction to CUDA prerequisites. If you're not familiar with C++, I highly recommend this chapter of this crash course, which is like not that long. It's probably less than an hour. Like this chapter 3 of this crash course by this guy, Elliot Arledge, I think that's his last name. Here's his LinkedIn and stuff. So all the credit to him. He made this awesome CUDA crash course that is like 12 hours. So obviously this is a more in-depth introduction to CUDA. But if you only want a C++ review, this one that he made over here is really awesome. So I highly recommend that one. Then after that, if you want a lighter introduction, I highly recommend this blog. That is the one that I'll be going over. So again, this post is a simple introduction to CUDA. We start simple. The first script, as you can see here, is about adding the elements of two arrays, right? So we have two arrays, array X and array Y. Array Y, right? The size is 1 million elements. In case you're not familiar with the notation, this is basically 1 bit pushed to the right to any spaces in powers of 2, right? It's playing in C++. So basically this means that you're pushing. This is 1 million in powers of 2, right? Right? It's like 2 to the 20, right? So that's what this means. So we have n equal to around 1,000,000 elements. It's technically more than 1,000,000 elements. It's slightly more than 1,000,000 elements. So yeah. So and we have this function here, add, the C++ function. So yeah. Okay, I actually think I'm going to code it up one line by line because I think it's nice to do that. So okay, so first we're going to run the C++ program, compile it, and let's see. But I think we're going to do it without the GPU. Yeah. So first we're going to do it without the GPU. Okay. So starting simple. Let's practice some C++. So the way you do it in Colab is like, you for example go here like get file, add cpp, so include iStream, those standard libraries, right? This one is for printing stuff, and this one is for math h, right? So we're going to have a function to add elements to arrays. As always, all the credit goes to this guy. Okay, so void add int and float x as a pointer, float y as a pointer. You know, this is obviously the same as this, right? Sometimes people write this like this, but the best style guides, in my view, try to emphasize that, you know, the pointer is specific to the declarator or the variable in this case, because in principle you can also declare stuff like this, right? You know, and only this one would be a pointer and this one would be a float value, variable, right? So that's why it's better to put the asterisk here to emphasize that you are attaching this to the declarator, which means this is going to be a pointer reference. Okay, in C++. So then we go for the for loop. Nothing surprising here, just a typical for loop. Right, I++, and this it's I times yi. Oops, sorry for the typo. By the way, an important concept here, I think it's worth mentioning. So well, it's obviously what you would expect, but just to be precise, x plus I, you know, like this is equivalent to xi, right? So x bracket I is shorthand for x plus I, and then differencing that, right? Is value of remind me what is the name of the operator? Yeah, it's no, it's not the difference operator. No, I meant difference or not. So yeah, right. This is the difference operator. Is the what operator? You just want to know. So address of operator, right? So the difference operator, of course. Differencing. So differencing so this is like the this is a pointer variable, so plus this many positions according to the yeah, basically this many positions in memory, I positions in memory, and then you difference that. That's how you would do it if you want to be super explicit with the pointer notation, but x bracket I does it for you in C++, just so you know. Okay, so initialize x and y arrays on the host. The host is the CPU, so I'm glad we're doing it this way because then I can explain. Right now we're using the host, so this is still a CPU, we're not using GPUs yet. So we're initializing this in the host, right? Oh no, hold on. I'm so sorry, we're not doing that yet, this is just a function. Oops, sorry about that. Now we're going to start with the main. In the main, we're going to initialize some stuff, right? Yeah, but we're going to do this slightly later, right? So the first thing I want to do here is to declare here, I'm so sorry I have this in Chinese, just look at that, that's funny. So, and my goodness, n is 120, right? 2 to the power of 20, sorry. Excuse the Chinese, my computer is crazy right now. So, right, as I explained here, right, like this big number, 2 to the power of 20, basically, or 1 bit pushed that many positions to the left. Oh, by the way, just so you know, what would happen if you do 5? So it means, right, it means 5 times 2 to the power of 20, just so you know, that's what it would mean, right? If you're curious, always good to learn the details. So now we're going to declare the arrays. Float x equals new float n, right, of size n. We're going to do the same with y, the array y. Now we're going to initialize the values, right? Here we just declare the variables, obviously, so we're going to initialize the x and y arrays on the host. We're still on the host, nothing to do with GPUs yet, right? Plus, right? And we add certain values. So it's going to be 1 for the array x and y for the array 2.0f, right? So this is the way to do it. We're going to run the kernel, right? What's the kernel? The kernel is basically this function we have over here. People call it a kernel in CUDA lingo, GPU lingo. So we run the kernel of 1 on 1 million elements on the CPU. I want to emphasize we're doing still this on the CPU. So we call the function add n. Let's use the production issues over here. So add n, yeah, and we pass the array variables, right? Don't forget the semicolon. So we're going to check for errors. All values should obviously be 3 because we're adding up the values in the arrays. Oh. So float maths error, I mean there should be no errors, 0f, right? For we check every position basically in in the resulting array to put it away, right? On y, because we're adding on y, right? So this function is not returning anything. We're just adding things on top of y. So this should be 1 plus 2 on the array y. So it would end up being all 3s on the variable. Again, because we passed by reference, that is like the pointers. So it's going to modify the original variable, right? So n I++, we go over every single position. So f max, basically, you know, we take the max error here, right? The maximum between f abs means absolute value. So we compute the error yi 3.0f, right? So we take the maximum value between the absolute value of this difference and this max error, which starts at 0 and hopefully stays at 0, and we assign it here. Right, std count max error variable here, std end line. This is standard C++ stuff, just follow along. Free memory, because we're using like the standard new and, you know, like keywords, we have to use the delete keyword, right? Just follow along. This is best practice. Probably doesn't matter too much for a Colab notebook, but still let's do it that way. Now, some important stuff for you to be comfortable doing this on Google Colab. Let's just learn how to actually run it on Google Colab, right? So we need to compile it. So shell, this is going to compile this as add, and then we just call add. Oops, what happened? Oh, we're missing a semicolon somewhere. Yeah, this happens all the time in C++. Okay. Oops, there's another mistake. Missing another 2 dots here. Oops, there's another mistake. Math error. What's the issue here? Let's see. So, did you mean maths? Oh, yeah. Oops. Make sure you don't make these typos. Yeah, so you correct the errors that the compiler told you about, and then again shell, and you call add. So the compilation is going to create this binary here called add, right? Out of the add CPP. So we call add, and the math error is 0. We run this in the CPU. We still don't have GPUs, but we're going to switch to a GPU soon. So that was great. Awesome, congratulations if you got to this point. So as expected, there was no error. That's great. But now we're going to run this in parallel, right? We're going to get this computation to run in parallel, right, on the many cores of a GPU. So the first step is to make the kernel function, right? As it says, a function to a function that the GPU can run. That's called a kernel in CUDA. So what we need to do is to specify the global keyword to the function, which tells CUDA C++ compiler that this is a function that runs on the GPU and can be called from CPU code. So that's actually not too complicated. For some reason they have this here. I don't know why. I think it's from a previous version of the tutorial. You can ignore that, I think. We don't need the sum here. Oh, by the way, I'm going to show you this. yeah, here. So there's also a notebook, by the way, of this blog that is official. You can also check it out. And here you can confirm that indeed that argument is not needed. We're not going to use it. Basically because in our version, which I'm following something closer to this version, we are adding the sum on top of the one of the original arrays that we passed as pointer, because it's just simpler for the purposes of this tutorial. So we're going to do it that way, right? So don't copy this as is. Actually, let's get this whole script. We're going to call it, let's follow this naming convention here. I really liked it. Oh, they call it add Q. Okay, I guess that's fine. I prefer to call it add CUDA, right? So that we don't get confused, actually. So add CUDA. Okay, so let's call it like that, add CUDA.cu. But we're going to add the keyword. That's really all we need first. So we're going to add the keyword here, and so we also need to, let's see, do some memory allocation thing. Yeah, because to compute on the GPU, it's not just like, oh, the keyword is for letting know CUDA that we can run that kernel in the GPU, that function. But we need to allocate memory accessible by the GPU. There are some details here about unified memory in CUDA, which speaks of, like it's for allowing both the GPU and the CPU to access some sort of unified memory. We need to call CUDA memory allocation, right? malloc memory allocation managed, this function to allocate memory that the GPU will need, right, for this, which returns a pointer that you can access from the host, the CPU code, or device, the GPU code, a memory address that both places can access, basically, right? A pointer is a variable that contains the value of a memory address, right? So to free the data in the end, we're going to use cudaFree. Yeah, it's the same basically, but we're going to use these functions that allocate memory in the right place, a place that both the host and the CPU can use. Okay. Okay. So actually, I'm going to code it up myself with my own hands. Just let me take a look at my notes here. Right. So just to see the linting, for a moment, let's do it this way. So here, right, instead of allocating memory like this, we're going to declare the variables x, y. Then we're going to say cudaMallocManaged address of x. That's interesting. We pass here address of x, not the pointer, because it wants the value as a reference. It wants the reference to x because it's going to modify our pointer, not a copy of whatever is in the pointer, right? Anyways, it's garbage right now because it doesn't have anything in it, but it wants the memory address of the pointer because it wants to modify the pointer content, right? It doesn't want the content of the pointer, it wants to modify the content of the pointer, so you pass the address of the pointer. That's basically it. Oops, no, right, so this is like this, but here we pass basically the size again, right? Size of float. So basically you want enough space for 1,000,000 elements, and you pass the correct size of a given float, right? So that's how we do it. Okay, so in the end is cudaFree, the same here, but for Y. Just very quickly, I'm going to ask ChatGPT, can you explain why here we pass the address of, not just X or Y? It's just what I just explained to you, but ChatGPT is going to show you the signature of the function, I think, most likely. Right, because pointer to pointer, right? So it's a pointer to a pointer, right? The first parameter is void pointer to pointer, right? In the div, yeah, it's basically that, a pointer to a pointer. What is a pointer to a pointer? It needs the address of data located in memory for in your variable. Explain what a pointer to a pointer is in one sentence, just that we close it. It's a variable that stores the memory address of another pointer. That's just what it is. So obviously you don't pass a copy of what it's in the pointer because it's just garbage. You pass the address of the pointer because cudaMallocManaged wants to modify it, right? Inside of the function, it's probably doing something like what is cudaMallocManaged string to the variable inside. So let's see. So inside is show it. My goodness, no, ChatGPT is not getting my question. Can you show what kind of line is being called inside cudaMallocManaged? Yeah, so probably it's doing something like this, right? Like it's grading the located address into your pointer variable, right? So it differences the pointer to pointer to retrieve the pointer and then modify the pointer. So this is like x equals address, right? So you differentiate it once and you get the pointer, x or y, and you set the address in that pointer, right? So that's what it does. I thought it was worth explaining. Okay, so, but how, this is not enough yet. Because obviously we need to send, to put it away, the computation. We need to launch the computation into the GPU. The way to do that is to, like I need to launch the add kernel, which invokes the CUDA GPU. That's what it says here. For doing that, we're going to use these triple brackets over here. We're going to ignore for now what the 1,1 means. Yeah, but basically that's the last step. We run the kernel of 1 million elements on the GPU, right? It's actually not the last step, I just realized. There's another step. So the other step is to wait for GPU to finish before accessing on the host. So CUDA device synchronize. The device synchronizes the devices, the GPU synchronizes before we keep going on the host, right? So yeah. So just one more thing, I need the CPU to wait until the kernel is done before it accesses the results. Before CUDA kernel launches, don't block the calling CPU thread. So we need to call this thing, right? It's very idiomatic, to put it that way. So we're going to do that before we keep going. There you go. So we're going to do the full extension queue, right? Don't forget that bit. And we're going to use a different compiler, right? It's not the same compiler, right? We need to use the NVCC NVIDIA CUDA compiler. So we're going to call this thing here shell There seems to be an issue. Oh yeah, sorry. Add CUDA. Yeah, because I followed this naming convention for the file. Add CUDA.cu. So we compile. Then we call add CUDA, write shell add CUDA, and it didn't work. Why it didn't work? What happened? Let's see. So it doesn't tell me much. Let's see, is there an issue here? This looks alright. Cu. Doesn't complain. Let's ask ChatGPT. Do you see an error here? Maybe I'm missing something. No, that's not the issue. No, let's see. No, I mean here. Let's see. Oh, I'm such a... I forgot to switch to runtime. Yeah, don't forget to do that. That's funny. T4 GPU. Yeah. Okay, so we go to runtime and we T4 GPU. Okay. Okay. This is why it's probably useful to record live on the struggle in front of thousands of people on YouTube. So okay, so now we call add CUDA and there's a match error 1. Why? Give me a second, I'm going to paste a very useful command. Okay, here I have another copy of my notebook from before. So I want to show you here how you can see errors. How you can see errors. Yeah. So there's this little thing here. Excuse that I'm not going to write it down. I'm going to just copy and paste it. Right here, for example. Right. Just so you can see it correctly. So it's CUDA error equals CUDA get last error. If error is not a CUDA success, we're going to print the CUDA error. This is super useful for debugging stuff, right? So we're going to compile again. Actually, see you. Okay, CUDA error. The provided PTX was compiled with an unsupported toolchain. What does this mean? It means that it didn't even use the GPU. It didn't use it. So the match error stayed in ones. You know, another debugging trick obviously is to print perhaps like a few elements of the array, right? We print like the first 10 elements. There is nothing more to it, so we're going to print right, like just print the first elements of y and try to see their values, and it's all 2s. So yeah, this line means that it didn't even launch the kernel into the APU. So why is that? So I did some research, and apparently is an issue here. Yeah, like if you check, apparently this can happen with mismatching versions of CUDA. Version is 2.4 here, but the other thing that matters is the right. So this shows you the version of CUDA in the GPU we are using. We're using the T4 GPU, Tesla T4, and it comes with the 12.4 version of CUDA. But the CUDA version that we are trying to use is actually 12.5. So for whatever reason, this has been a common issue since early 2025. I'm recording this in September. Oh my god! People are complaining, right? Because this guy is saying that the upgrade to 12.5 decimated their working system, right? So it's a common issue with an easy solution. So this guy over here called Shashank Shekhar with this very funny blog, he took the time to explain. He gave the solution here. So basically, use the kind of architecture or that doesn't rely on PTX. CUDA 12.5 relies on PTX, so we're not going to use PTX. So yeah, so right, he gave the correct command. What is important for us though is you can do it this way, right? Yeah, you add this flag here, architecture SM75. I don't think you need to care too much about the details, but if you are interested, read this blog. Anyways, so if we compile like this, we're not going to use PTX, which seems to be a new feature of CUDA 12.5. And now we run this, and there's no error, right? So I struggle with that a bit. So I'm giving out here the tricks so that you can run everything perfectly on Google Colab. Okay, we're doing really well so far. Okay, great. Okay, so what's the next step? It says something about the race conditions. I'm going to skip that. You can read about that here. I don't think it's super essential. I want to focus on the core things that can get you comfortable with getting a sense of how to use CUDA. So we can profile it. This is a good way to profile it, and I'm going to do it this way. He has a script that gives you less information, but I think it's the same thing. So I think we should use like the nsys profiler as it is. So to do that, it's basically just the same as running it, but with the profiler, right? What happened? Add CUDA profile tcuda. That's true. nsys not found. Do I need to install it? Really? I wasn't expecting that I would need to install it. I don't remember having to install it before. Cannot call nsys on Colab. So it doesn't ship with the Nsight Systems. So how do I install it? Of course I can. Yeah, so probably what worked for me before and I didn't realize it is that I installed the CUDA toolkit apparently. So try to do that. Okay, that took a while, but I tried to install the toolkit because apparently that comes with the Nsight profiler. NVIDIA is what's the name of that thing again? It's Nsight Systems profiler, right? So let's try actually. Yeah, now it works. It's how it is. You would think that at this point Google Colab would come with all of this already. So nsys profile, and we run it this way. And the line that you care about is where you see here the function, our kernel. And we have the total time in nanoseconds. So you take 6 units, and so you take 3, it's microseconds, you take 6, it's milliseconds, right? So it's 109 milliseconds. Yeah, that's what it takes. 100 milliseconds, that's what it took. We ran it in the GPU though, but we ran it all in one thread anyways, right? Because at this point you should guess it wasn't really, we didn't really run it in parallel. We just launched it into the GPU in one block, one thread. So, right, like one thread that does some computation. But how do you actually do it in parallel? Well, we need to, for example, we're going to choose 256 threads, right? So we're going to declare that over here, right? So let's copy and paste this here. Okay, so we're going to call that, what's a good name for that? We can take inspiration from their notebooks too. Block. Yeah, that's okay because we're going to be running it in a block, right? Right, one block with multiple threads. So we're going to call this, for the moment, VP add block, because we're running 256 threads in one block still, right? Now we need to make some changes though to our code in order to leverage the threads. So how do we go about that? So the key thing to keep in mind is here we're going to do something called striding. Yeah, we're going to stride through the loop, right? Through the computation. Yeah, because it says if we run the thing right now with only this change, it will run the computation once. Oh, that would be terrible actually. It will run the computation once per thread, rather than spreading the computation across the parallel threads. You don't want to run the computation like one per thread. Yeah, because you will be sending this function to every thread. No, sorry. You will be sending our function to every thread, and that's just going to run the computation in every thread. So it's actually more work. No, you want to send a different function to every thread that knows what to compute, right? You want to spread the computation across parallel threads. So to do it properly, we're going to modify the kernel, And CUDA C++ provides keywords that let kernels get the indices of the running threads. Specifically, thread IDX, which is obvious what it means. It means get the index of the thread you are at. It contains the index of the current thread within its block, perfect. And block dimensions, the size of the block, contains the number of threads in the block, right? Yeah, the number of threads in the block. In this case it would be 256. So we are going to modify the loop to stride through the array with parallel threads. And how do we do that? Let's see. So we're going to modify the loop. So first of all, we're going to get here the index of the thread. So it's going to be thread IDX .x, and the stride is going to be the size of the stride is the size of the block, which in this case is going to be 256 because that's what we are assigning over here. So I is going to jump this stride size, and obviously we have this maximum here so that we don't overshoot, and that's it. Why do we do it this way? Why don't we chunk? You know, if you think about it, oh wait, no, and we start in the index, right? We start in the index. Obviously it wouldn't make any sense. So for thread 1, this is going to start at I equals 1, and then I equals, well, actually let's say 0, then 256, 250, I equals 256 times 2, right? And so on, right? 0 plus that, actually, right? But not to make it confusing, so if it's the thread index 1, it's going to be 1, then it's going to be 57, or just like that, right? And so on. This is different than chunking. Chunking would be another strategy. Chunking would be different. It would be the first 256 going the first thread, the second 256 going to the second thread, and that actually would work. But it's not the cleanest or more recommended way to do it, and ChatGPT is going to quickly explain us why. Can you explain the concept of striding and compare it to the alternative of chunking? Explain why striding is the common way to go. Okay, so I just pasted that. So this is a classic CUDA pattern that we have landed on. Perfect. Okay, I'm trusting ChatGPT is going to give a good explanation. So the thread's starting position and how far apart the next index is. So thread 0 indices 0 to 56 and 512. Thread 1 indices 1 to 57, 513. Thread 2 is 2 to 58 and 514, etc. So the work is interleaved, weird word, whatever, across threads. Chunking, the alternative. Okay, so chunking is the alternative. We could have calculated the chunk size like this with this little function. The -1 is just to sort of like do integer division that doesn't underestimate the proper chunk size. This is just math here, standard math. There's a reason why this is how you do it without overshooting, right? It's like the upper floor of the integer division. So anyways, but you calculate the chunk size. You get the thread ID times the chunk size. That's going to be your starting point, and the end is going to be the minimum between the start plus the chunk size, or the maximum number of values, because you don't want to overshoot, right? So this is how you would do it. First chunk from 0 to 255, second chunk to 256 to 511, and you keep going like that. It's grouped. The work is grouped into contiguous blocks. But why is striding universally preferred? There's this concept of memory coalescing, and basically what you need to know is that the GPUs fetch memory in a... So, how to put it? There's a better way to put it. So, yeah, so the concept is that GPUs prefer to access consecutive elements of the array. You know, so can you illustrate this? I am not saying it, right? So let's focus on this part, right? GPUs prefer to access consecutive elements of the array. So my goodness. Yeah, right. So in the first computation, because it's running in parallel, or as parallel as possible, thread 0 is handling 0 index, thread 1 is handling the 1, thread 2 is handling the 3 index, and so on, right? And thread 3 is handling index number 3. I like this. But like this, but can you do it with the 256 stride we have? Yeah, that's an example, but it's not like our example, right? So here, so thread 0 has like 0, thread 1, thread 2, thread 3, and so on. In this quote-unquote first parallel run, the hardware actually does something different sometimes, but that's another topic. From an abstract perspective, the idea is that if it were truly parallel, in the first quote-unquote parallel run, you go through the first stride, and the second parallel run, you go through the second stride, and so on. So you see here how you are satisfying the memory coalescing concept by having the running the consecutive elements, right? So the 256 consecutive elements in memory, right? Right, because in the arrays are real. Like in memory, there have positions in addresses that are one after the other, and GPU seem to like accessing things that way, you know, like the first thread is handling something that is next to the second thread in the memory address, right? And so on. So this is the brilliance of striding like this, right? I hope that gives you the intuition about why it's the case. It's also cleaner in my view, you know, like the code. Once you get the gist of it, it's even cleaner. Because instead of doing this weird thing to compute the end, you know, this is taken care of. Like, you don't overshoot ever because of this condition. Okay, so that explains the concept of striding, which we already took care of over there, and I think that's all we need to give it a run, right? So yeah, let's try it out. At blocks CU. We're going to get our compiler line here, shell add block, and I'm also going to get the profiler line here. Make sure you actually get the names correctly here, right? Block. It's all add block. So let's give it a shot. Oops, something went south. Oh, we're missing a... Yeah, let's do this in different lines, so that we don't get confused about where it failed. So, okay, so anyways, it failed in the compilation. So we're missing here a semicolon, right? Okay, we compile correctly, and there you go. It's all good. But now the total time of our kernel is about 3 milliseconds. Look at that. 3 milliseconds. And that's very good. Before it was like 100 milliseconds. It's almost 4 milliseconds, but that was amazing because we ran things in parallel. Now we're running everything in one block. Because it seems that one block in an NVIDIA T4 GPU has like over 1,000 threads, and we just use like 256 threads. So, and we only we didn't actually use the block ID. We didn't need that, right? As you saw in our code. But later on, we're going to use the block ID too. So this part over here is called out of the blocks. So what is that all about? So from an abstract perspective, so this talks about NVIDIA cores and streaming multiprocessors. This is the hardware. One streaming multiprocessor can support about 1,000 threads. But it all depends in the end about how you define it. So for example here, if the block size is 256, one streaming multiprocessor probably could hold about 4 blocks, I guess, right? Because a streaming multiprocessor can hold a little over 1,000 threads. Now this is hardware, so forget about that. You don't care about that right now, because when you are coding in CUDA, you actually care about abstraction of parallelization, right? When it comes to the abstraction, you don't care about whether the streaming multiprocessor, which is the hardware, is going to run this number of blocks in parallel. It's going to do it if it can. It depends on the size of the blocks. But you don't care about that. You care about the notion of a grid, which is an abstraction. A grid is, in this hierarchy, an idea, an abstraction that holds a certain number of blocks, as you see here. That's what you care about. So for example, together the blocks of parallel threads make up what is known as the grid, right? So the first parameter specifies the number of thread blocks. The first parameter here, right? Number of blocks and the block size. We already covered the block size. Now we're covering the number of blocks. So the number of blocks, in this case, they decided that the appropriate number of blocks is basically based on the number of elements we have divided by the block size, plus this approximation trick that we have here. But it's basically the number of elements that we want to cover in the computations, right? Divided by the block size. It's going to give us the number of blocks. So that number seems to be about this, about 4,000 blocks, and that's going to be our grid. But the grid is not hardware. The grid is an abstraction. The hardware, in fact, can't handle that many blocks running in parallel because there's a hardware limit, right? It has 40 streaming multiprocessors with this many cores. The cores is even something else, like it's kind of irrelevant for us right now. What you care about is this parallelization concept. I'm going to have more blocks across a grid of a size of 4,000 blocks, right? So that's what you care about. So to get out of the block, one block, and have it across many blocks in our code, the index must account for the block ID so that we know where we are at, right? So the block ID times the block dimension plus thread IDX, right? So the index, this explains it perfectly, right? So to know this position, it's 0, 1, 2, block 2 here, block ID times the block dimension. So that will gets us from 255 times 2, that's about 500 something, and that's not enough. We need the thread IDX. In this case is about 3, so it's plus 3, right? And that gives us 500, 5, which is 515, right? This is the index that you see here highlighted in yellow, dark yellow. So this is what this line is doing to know the index, the starting index. And the stride is now the block dimension times the grid dimension, right? But so that we can see it, let's ask ChatGPT. Can you illustrate it visually with these assumptions? Okay. I want to see this stride. Multi-block striding version. So the block size, the number of blocks, the size of the stride. Wow, it's a very big stride. But we should ask ChatGPT, but why are we shooting for 2 million if the number of elements was 1 million? So that was our number of elements. Total threads. So each thread starts in this range. Then it adds a stride that is quite huge, actually. Yeah, it's a little stupid now that I think about it. So if we spread the computation across all of it, the stride is going to add up to I guess over the threshold very quickly, but it ends anyways. The loop ends. So why do we have the stride at all? I guess it's so that the kernel generalizes, which is a good point. If we increase the end, but it still launched this many threads, hypothetically. I wonder if we increase the size of the grid, but whatever. You know, then it would work like it worked before, I guess. But right now, it basically finishes in the first iteration because we're spreading the computation almost perfectly in the first iteration across all the possible threads, at least in the abstract. That's the real concept. In the abstract, that's what we're doing. The hardware may need to schedule things a little bit because there's a limit of how many concurrence blocks you can run. But anyways, I think this clears it up visually very well. Yeah. I had this question in real time, but I think it was worth it. So okay, so those are the changes that we have to make. So let's do it. I'm going to copy and paste this. CPP. Let's put grid. And so excuse that I'm being a bit lazy here. But I think you get the points, right? So again, the block ID and the block dimension and the thread ID to know where we're starting at here, and the size of the stride. That's not all we need. Remember that we also need to get the block size and the number of blocks, right? So here, right, so we still have 256 threads for the block size, but we compute the number of blocks, which is basically the total elements divided by the block size, and with this approximation trick, and now we're ready to launch it. Oh, but I want to name it here, like Q. And we compile it. Yeah, no mistakes there. And we run it and profile it. And there you go. Now it's total time is 2 milliseconds, which is not too much improvement. Going from 3 or almost 4 milliseconds to 2 milliseconds, that's not much improvement. And that was to be expected. Well, that's interesting. The guy over here, Mark Harris, said that's interesting. There's no speed up from this change. And in his version, it even was like a possibly small or slight slowdown. Why is that? If increasing compute by a factor of 40, the number of semi-hypers streaming multiprocessors doesn't bring down the total time, then computation was not the bottleneck. So it's true that we spread the computation even more, at least from the abstract, because in the end it's constrained by the hardware. But in this case, the computation was not the bottleneck. There may be other bottlenecks. In this case, it's about memory prefetching. So here it explains a few things about memory prefetching. But what I want you to know is that prefetching makes sure that the data is on the GPU before the kernel needs it, right? That's the gist. You can read more about the details here, but prefetching is to make sure that the data is on the GPU before the kernel needs it. Otherwise, the kernel is going to keep checking the data on the host one by one, and that's slow. That's the gist. So this line is to make sure that we have the data in the GPU before the kernel even needs it, as opposed to reading or getting the data from the CPU, asking for the data in the CPU every time. So that's the gist. I'm going to just please explain this with no jargon anyways. Please explain this with no jargon and concisely. It's basically about having the data on the GPU device instead of asking one by one for it to the host. So that's what it's basically about. So by default, unified memory moves the data between CPU and GPU only when it's first touched. Yeah, right. So by default, like the GPU has to pause and pull in pages of data. That's jargon. But it's basically the data one by one, very slow. So prefetching tells CUDA, hey, move these arrays to the GPU now before the kernel even runs all of it. That way, when the GPU starts working, the data is already there. So that's about it. So we're going to use prefetching, and I think the right place for that, should I just do it here? Yeah, let's just do it here on add grid, whatever. I'm not going to create a new file for that. But basically you want it here before you call. Yeah, let's prefetch here, right? To emphasize, that we're going to do it there, right? We prefetch the X and Y arrays. Well, I guess it's cleaner if we do it like this. It's the same thing. So yeah, well, we prefetch the arrays into GPU. Okay. So that didn't cut the time too much. Oh, did I make a mistake? Yeah, it should have been like a big improvement. What did I do wrong? Did I put it in the right place? Well, that's interesting. What's going on? Add grid. Oh, oops. Yeah, sorry. I was creating a new file in the end of the day. Yeah, addgrid.cu. We recompile addgrid.cu. And indeed, again, these are nanoseconds, so like 3 units out. That's microseconds, 54 microseconds. Not even a millisecond. 54 microseconds. That's super fast. A millisecond is very fast. Very, very fast. It's not even a 100 microseconds or 200 microseconds or 500 microseconds or 900 microseconds. No. It's 54 microseconds. That's very fast. Mind-blowing. Performance improvement. So summing up, here it gives you certain proportions for the improvement. I think the key proportion here is going from 45x to 1932x, because it says that once the data is in memory, the speed up going from a single block to multiple blocks, right, from a single block to multiple blocks, is proportional to the number of streaming multiprocessors, 40 on the GPU, right? So the proportion here is about 40. You can make the division, it's about 40. Yeah. And you can always read more details here. But this tutorial shows how to parallelize on the abstract across a thread, across blocks, and therefore within a grid, and gives a few concepts on the speedups regarding the hardware, connects it a little bit to the hardware, but it also gives the tip of prefetching things into the GPU so that you make the most of the hardware, of the multiple blocks. Exercises, I was hoping we could do some of them, but I think this tutorial is already long enough, over an hour. Try to experiment with preempt commands inside the kernel. Try to print the values of thread IDX, block IDX for some or all of the threads. Do they print in sequential order? Well, no, why not? That would be interesting to try out. Yeah, that would be interesting. Would they print in sequential order? Probably not. Because of the strides, they're going to print in close ranges, right? Probably it's going to be, in the case of a single thread, it's going to be the first range of 1 to around 256, because the parallel threads are going to stride through that. But because of race conditions, and this is an issue when you run things in parallel, race conditions. Remember, that's why we synchronize here, because there are race conditions too. Because of race conditions, it probably is not necessarily in perfect order. So that's what I would expect. And a few other interesting questions. Could be worth covering in a future video. Maybe a very short video. Okay, so again, that's the tutorial. I'm going to clean up the code here a little bit. Well, I don't need to clean up the code. I probably should just link this notebook that they have. I'm going to link this one perhaps and a clean version of my own, because I do need to give tips about how to install the profiler, how to overcome the issue that we saw here, and obviously I'm going to give credit to all the sources. In the future, I'm going to try to make a tutorial about these boring topics. Here, I think this should be one tutorial, all of these boring topics. Yeah, all of this. Then there should be a tutorial about scientific computing and AI for science, or just scientific computing. This is not AI yet, really. So this should be a scientific computing tutorial covering these three blocks. And this other topic here, for some reason, is at the end. We need to check it out too. Obviously, all the credit goes to Mark Harris, a distinguished engineer at NVIDIA. Mark, if you saw this, thank you. If you watched this, it was an amazing tutorial to follow. Very skilled person, a professional. He's the one who made this blog that we just covered and went all over to learn a few things. As always, if you have any questions, please comment below. My LinkedIn is there. If you go to my website of techcontext.com, you can also set up a call with me, actually. You can also do that. I help teams with scientific computing and AI for science and physics-informed neural networks and physics machine learning. I have skills, obviously, in the data science side of things, in the neural network side of things, in the PyTorch side of things, in the CUDA side of things. But I also actually have strong skills with full stack web development, front end, back end, you name it, cloud stuff, databases. And I can handle agentic AI as well, very well. AI agents orchestration, there's a video of that in the context, let's see if you find it. Applied in the context of AI for science. And I also have a strong experience with Kubernetes and AI infrastructure, Terraform, you name it, to run GPUs in the cloud. There's a few videos about how to use Docker to run GPUs on Google Cloud and AWS on my channel. So if you want to collaborate, just hit me a message and we can sort something out. I would love to help teams make the most of AI for science, physics, machine learning, and scientific computing for their scientific or engineering applications. I'm all ears. I would love to learn about your use case and help you out. So just reach out and we can sort something out. Small team, bigger team, whatever. I'm here to help out and learn a lot with you too, because I also enjoy diving into this use case of the industry. You know, some people have reached out before from some cool companies like BMW and Bosch, and it has been a joy to help them out too. So let me know, and don't forget to subscribe. Bye.